Okay, here is what we're going to do today, all right? We're going to do some things on the notes right here, and then I want you to explore on your own through Desmos, okay? So here's what I want you to do first. I'm going to give you a couple different equations of exponential functions. Okay, let's try and get back on track here.
Wait, are we in math class?
Yes, we're in math class. Okay, so I am giving you a parent function in the form of y equals b to the x. The example of the parent function of which I'm giving you is y equals 3 to the x. So you'll notice that there is a 3 to the something in each of these bubbles that I have down here, right? So I have these 7 bubbles. Does that sound good to you? Here's what I would like you to do. For each of the bubbles here, I would like you to go to Desmos, which is right over here, okay? And we've already plugged in 3 to the x. You see that? This is going to be our parent function, and I kind of want to make this one black so that I keep it there. And then I also want to make this thing projector mode so that I can see it. Okay? And then the 2 points that I think that we should put on there are 0, 1. Whoa, that's not right. Are 0, 1. So I'll do 0. Oh, no, let's go back. Okay, so right here, shift 0, 1. And notice that point would be there. And then the other point that I think we should put on there would be what? 1, 1, what would be the output, you guys? 3, very good. Okay, 1, 3. And then I would encourage you to kind of make these black as well so you can see them. All right? Just like that, you hit the, yeah, you hit this thing here. Okay, so for each of, now let's take a look at this, all right? This is our basic parent exponential function, 3 to the x. And in fact, you know what? We might want to even make this thing dotted so we can compare it to everything else. Okay? So I'll put that away for now. So we already know a lot about this graph. We know it has an asymptote at y equals 0. We know we have these 2 anchor points that are guaranteed to be on there. Okay, we're starting with this. This is an example of a parent graph. Everybody cool so far? Sweet. Here's what I would like you to do for your task right now. I would like you to graph each one of these little 7 bubbles, and I would like you to compare it to the parent graph and write a sentence or a statement as to what the effect of the 2 is going to have on the parent graph. What is the effect of the 1/2 going to have on the parent graph? What is the effect of a negative 1/2? And so on and so forth, okay? That's what I'd like you to do for an exploration right now. Does everyone understand the directions? One together. All right. So here's what I'm hoping that you'll see, all right? Yeah, what do you think? What's going on? Right? How has this been, how is the orange graph compared to the black graph? Is it compressed? Is that the right word? It gets stretched. Yeah, it gets stretched, okay? So something that you could say for this one over here would be it gets stretched by a factor of what? Very good, by a factor of 2, okay? So I would like you to explore all of those right now, and then we're going to come back as a class and talk about them. So next 5 minutes, explore all of these. Ready, set, go. Hopefully you had a chance to explore some of those and you have some answers back there. Yeah, bro. Yeah, okay. All right, so these are the kind of the words that I was going for you guys to sort of discover: a stretch, a shrink, a reflection, left or right, and then up or down. So what did you guys notice about, we already did the first one, so let me zoom into this, okay? What did you guys notice about 1/2 3 to the x? Anybody notice anything about this one? This one, 1/2 3 to the x.
It's moved down 1 unit.
Yeah, this is going to be our shrink. Okay, we're going to talk about that one. That's going to be our shrink. What about negative 1/2 3 to the x?
Reflection over x.
That's going to be our reflection over the x. And also a shrink, and we're going to talk more about that one in a second. Okay, what about 3 to the x plus 2? What'd you come up with that for that one? Yeah, this is going to move to the left. How many units? 2 units. Very good. What about this one over here? 3 to the x minus 4.
To the right 4.
To the right. Very good. Right, 4 units. Awesome. And then what about this one over here?
Move down 7. Oh, no, oops. Move
Up 5 units. Good. What about this one over here? Down 7 units. Okay, you guys got this pretty darn good. Okay, so let's go over here and talk about, in a more abstract concept, what it means to do a stretch. Okay, so whenever we have something that looks like this, y is equal to a times b to the x, where the absolute value of a is greater than 1, that is going to give us a vertical stretch. So this is some good information that you might want to have down here. All right. So when the absolute value of a is greater than 1, for any of these generic parent functions, we're going to get a vertical stretch. And the example that I gave you was 2 times 3 to the x. So I'm going to explore that with you right now. Notice I've shut off every other one. You can turn these off, by the way, right? You know that. So I've shut off every one except for the orange one here. So what we've done is we have increased the output by a factor of 2. So instead of 0, 1, I'm going to have the output of 0, 2 times 1, which would be 2. Instead of 1, 3, I'm going to increase the output by a factor of 2. So I should have the point 1, 6 on my orange graph. And look, there it is here. Whenever I go to that, that's the point 1, 6. If I get it close on there it is. You guys see it? So that's what that means to be a stretch by a factor of a if your a is greater than 1. Now, what about a shrink? Okay, we could have this. Y is equal to a times b to the x. But if 0 is less than absolute value of a, less than 1, we're going to get a shrink. Okay, and the example that I gave to you was the 1/2 3 to the x, because the value of a is a half, which would be between 0 and 1. Does that make sense to you? Okay, so the exploration that we have here, whoa, come back to me here. This one over here, I'm going to turn this one off and turn this one on. Okay, so you'll notice the difference is here is that this is half the output. Instead of 0, 1, I'm going to have 0, 1/2. And the shape of the exponential function is what we call a vertical shrink. Is that cool? Does that make sense to you guys? Yeah? Right on. No big deal. Okay, turn that one back off. Go back to our notes. Let's talk about a reflection. If I give you y is equal to, a times b to the x, if a is less than 0, we get a reflection. So which one of those corresponds to this? Well, that would be this one here, right? The negative 1/2 3 to the x. We're going to have a reflection, and we should also mention that this is going to be a reflection in the x-axis. All right? So the one that we can see clearly for this one is here. So notice that this one has been reflected in the x-axis, but it also has been something else. It's also been compressed, right? Shrunk by a factor of 1/2, right? Yeah.
Are the terms compressed and
Shrunk, same thing. Yeah, compressed and shrunk by same thing. Yep, absolutely. So we have that compression and that shrink, okay? All right, next on our list is left and right. So if I gave you, I'll go back to black to make sure we're in the same color scheme here. So if I gave you y is equal to b to the x plus or minus h, all right? So notice where the exponent is, and notice where the value of the exponent that I'm adding or subtracting from is. It's all up in the exponents here. So the two examples I gave you were 3 to the x minus 4 and 3 to the x plus 2. So let's explore those real quick. So here's 3 to the x plus 2. How does that compare to the black graph here? Well, it's just been moved 1, 2 units to the left, right? So at negative 2, I have 1. And then at negative 1, I have 3. You see that? So it's been moved exactly 2 units, 1, 2 to the left.
So if there's a plus in it, then it's going to be...
Yeah, it's the opposite direction that you'd think it is, right?
If it's a plus, it's left.
Yeah, exactly. And then here's the other one. Okay, here's 3 to the x minus 4. Notice it's been moved 4 units to the right. So it's been moved exactly 4 to the right. So we should write that down in our notes here. We should say, okay, so it's going to go to the left if the answer in my exponent is positive, to the right if the expression in my exponent is negative. Does that make sense to you? Okay. And then finally we have up and down, and it was of this form, y equals b to the x, and then plus or minus k. So if I'm adding plus or minus k on the outside, then it's going to be up or down. And this one is exactly how you think it was. Up if it's positive, down if my k is negative. So it works exactly as you think it would. The examples here are 3 to the x plus 5 and 3 to the x minus 7. So I'll turn these ones off, and I'll turn this one on. Here's 3 to the x plus 5. Notice, how does it compare? Well, it's just been moved 5 units up. Right there, right? 0, 6.
What would the asymptote
So the asymptote would also be y equals 5 in this case, because it's been moved up 5 units. So watch here.
Oh, so the
Yeah.
asymptote,
Y equals 5. Notice my asymptote goes up with it. Okay? So the asymptote does move when you move the graphs up or down. Okay?
So if you put a k value in, then the asymptote
Is going to be the k value. Yep, absolutely.
So it equals k value
Yeah.
for all of these, or what?
Yeah, exactly. So let me turn off this one and this one, and let's see if we can figure out the asymptote for this one. Okay? I'll zoom out a little bit. So this is the graph 3 to the x minus 7, so what should the asymptote be?
y equals 7.
Y equals negative 7, and look, there's my asymptote. So it does move with the graph. Alright, so I'm going to show you how I want you to graph these on your homework, on a test, on a quiz, on the final, for everything that we're doing, okay? I do not want you to just plug it into Desmos and then copy your screen. That's not what I want you to do. I want you to be able to look at this and tell me exactly what's going on. So there are two things that are happening, so let's talk about them. The two things that are happening are right here. Name one thing that this negative 1/3 does. Yes, I saw Rachel's hand first. This is a reflection over the x-axis. Awesome. And then I think I saw Mia's hand too. What else does it do, Mia?
It's shrinking.
It's a shrink. By how much?
By 1/3.
Very good. By 1/3. Okay? That right there is a conceptual understanding of what it means to transform our exponential functions, okay? Now, here is how I want you to graph it, all right? Then this is what I want you to do every single time. You are going to, if you have colors, colors are going to be great. If you don't have colors, then you're going to use a scale. I'm going to show you mine with colors. So I'm going to choose to use black for the first one. So the very first thing I'm going to do is I'm going to graph y equals 3 to the x, and that's going to represent my parent graph. Does that make sense? Okay. So the points that I have are here, 0, 1, and 1, 3. And those points are clearly marked on my graph. And I might even want to label them. 1, 3, and 0, 1. Okay, that's my parent graph. The second thing that I'm going to do is I'll pick a different color, and I'll go over here and I'll say y is equal to negative 3 to the x. So I'm doing one transformation for one color. Okay? So now, what is that negative going to do to my graph? It's one of these two things. Is it this one or is it this one? It's going to reflect it. Okay, so I'm going to do that. So then, this point will become here. And in my new color, I would label that point as 0, negative 1. And then this point would go down here to the point 1, negative 3. And then I would have this graph here. Very good. And then lastly, the third thing that I would do is I would graph y equals negative 1/3 times 3 to the x. So what is that going to do? It's going to shrink my graph down, right? So I'll zoom in as much as I can here. Very cool, right? So instead of 0, negative 1, I would have 0, negative 1/3. Okay? And instead of negative 1, or sorry, 1, negative 3, I would have a third of that, which would be 1, negative 1. So the graph that I would be looking at would be looking something like this. Okay? And that is how you would graph that problem on a test, quiz, or homework. I forgot to mention that the asymptote also would be on the final graph, and it would be here, and we would label it as y equals 0. So the question was, we have to use different colors. This could just be graph number 1, graph number 2, and graph number 3. All in the same color.
But we have to have all 3 graphs.
You have to have all 3 transformations, yes. Yes, you do. Here you go. Graph using transformations, 2 to the x minus 4. Let's talk me through it here.
Like
What
I know what we know.
what does that mean? What does that mean?
It's 4 to the right.
Yeah, 4 units to the right, okay? So here is how you would do this, okay? This is what I expect you guys to be able to do, all right? So the parent graph, number 1 would be y equals 2 to the x. So 1, or 0, 1, and 1, comma 2. And then you would have this, and we're good with that. Easy? Yes? Hello?
Yes.
Yes, good. Then take each of those 2 points you have and just move them 4 to the right. 1, 2, 3, 4. 1, 2, 3, 4. And then you'd have this. Boom. And then for the very final graph, we would also plug in the asymptote, and that would be the line y equals 0, and you'd be done.
It's always gonna have the 0 probably.
Yep. All right, ladies and gentlemen, how many of you have ever heard of the number pi? Who's heard of the number pi? 3.14, blah, blah, blah. Okay, now, pi. Now, pi is the most famous transcendental number. It's the most famous irrational number. However, the second most famous irrational transcendental number is this number e, which is called the Euler number, named after the person who started discovering it. So, if I take a look at this expression, 1 plus 1 over x, and I raise it to the exponent of x. If I take a look at this expression here, and as x approaches infinity, meaning that as x gets really, really big, this expression approaches a certain number. And the number that it approaches is this, 2.718, and it keeps on going forever and ever, just like it does, just like pi does, same kind of thing. So we approximate this to be e. So e is approximately 2.718 and then some change. Now I realize that's not a very good job of explaining to you what e is, but all it is looking at the numbers as x gets really big of that expression right there. That's one way to approximate e. Okay, so why do we care about this? Right? Well, e shows up a lot in exponential equations and in logarithms and in learning how to compute compound interest. Okay? So the last and final box here that we're going to talk about is something called continuous compound interest. All right? So we saw before, like yesterday, we had this, right? We had a of t was equal to a times 1 plus or minus r to the t, right? We saw that one for the interest? Okay, now, that is fine. You can use that formula for whatever you're, for doing very simple interest or interest that is compounded annually. For continuously compounded interest, we have a different formula. And the formula that we use is this. Our amount is equal to P, our principal, so that's what we're starting with, E to the RT. So some people heard this as A equals PERT, P E to the RT. So let me tell you what all these things are, okay? It's very simple. A is your amount that you're going to end up with.
Is PE its own thing?
P, this P right here is your principal or that you start with. Yeah, it's kind of like A, exactly. R is your percentage rate as a decimal. Your percentage rate as a decimal. Okay? And then, of course, T is your time in years. Okay, so we have all these pieces. Oh, and then there's this E, right? Well, E is just E, which is approximately 2.718, blah, blah, blah. There's a button on your calculator called E. I'll show you where it is right now. Sorry, hold on. Let me move this down a little bit. Yep. So, the E button on your calculator is right here. If you go second divide, notice when you push E, there you go. You get 2.7 and then some change. Okay? Yes. So, let's say we have $3,000 in the savings account. It's compounded continuously at 5%. How much will we have in 7 years? Yeah, so the A is going to be P e to the RT. And the reason we know we're going to use this formula is because it's compounded continuously. So A is going to be 3,000 e to the rate, which is 0.05, times t, which is 7 years. So we can just use the calculator for that one. Yeah, you're welcome. So when I plug in, I'm going to go 3,000. Parentheses, I'm going to go second. Check this out. This is the trick. Second ln gives you e, which is down here by the 4. Second ln. It gives you e and then the exponent. And the exponent, I know I have 0.05 times 7. And then if I get myself out of that and close the parentheses, I should get, after 5 years, or 7 years, $4,257.20. So approximately 4,000, what was it? 257? 257 and 20 cents.